welcome everybody to Lecture 10, Information Retrieval in the winter semester 2022, and now for some time already, 2023. I will say something about your experiences with exercise sheet 9, which was about beautiful linear algebra, latent semantic indexing, eigenvectors, and so on. The official course evaluation has started. There will be more information next week, but feel free to do it already. But if you do it already, here's some basic advice. Please take your time. You have taken so much time for the lecture, listening, doing the sheets. You can take some time to do the evaluation, like 20 minutes, I think, is an appropriate amount. Be honest and also be fair. So if you do the evaluation, you should have slept well, the sun should be shining, and you should feel in a generous mode, like you want others to feel towards you. I think that's then a fair attitude, but I will say more about it next week. And today we will talk about classification. I will say a few general things about classification, a bit as usual, since the math for many of you is some time ago and you forgot much of it. There will be a little crash course in probability, and then we will talk about naive Bayes, which is a very old, basic and simple learning method, but very good to learn a few things. And the exercise sheet will be, you get some movies, and I will talk more about it, and then just from the description of the movie, you should predict the genre, whether it's comedy, documentary, horror, romance, or science fiction. So what about the last exercise sheet, latent semantic indexing? Most of you found it very interesting and quite doable, with few exceptions. Nice, definitely help for understanding the lecture. Very interesting. Matrices are more fun than logarithms. The math sheet I enjoyed the most up to this point. Several of you said that it was nice to improve the mental arithmetic. I cannot emphasize enough that doing calculations in your head has benefits way beyond doing calculations in your head. So like 2-digit number, 17 times 36, doing this in your head. I mean, it's mathematically simple, but it's a great training for so many things, for doing things in your head, for focusing on something, and it will also, as a consequence, improve your math skills. I cannot emphasize enough. If you are, for some reason, not good at it or you have problems, practice it. It's something you can practice, like muscle work. My God, I hate pen and paper math, but it got better, so there was at least a silver lining. Took a long time, mixed feelings regarding calculations. I think, yeah, just take it as an opportunity to practice. Fun doing linear algebra and seeing the practical uses. A world without eigenvectors would be pretty eigenartig, wonderful German word. It's a shame that in modern capitalist societies, everyone only thinks about their eigenvalues. That's a very good one, I think. Why are several of you asked, and why do eigenvectors crop up everywhere, in learning, computer science, mathematics, physics, everywhere? They are so universal. Why is such a very theoretical construct so universal? One can give, I think, a whole course about this, but let me give you a very short glimpse, maybe. Again, I said some things in the last lecture. So what eigenvectors and eigenvalues characterized is what a matrix does to the space. Yeah, so a matrix, if you have a matrix, and let's take a symmetric matrix, it's a linear mapping and it does something to the space. It distorts it somehow. Maybe it rotates it, maybe it stretches it. It does things to the space. And what the eigenvalue theory does is that at least for a symmetric matrix, what every such linear mapping does is that you will have, for example, this three-dimensional space. Take any linear mapping from a symmetric matrix, then it will stretch the space by a factor of 3 in this dimension. It will shrink it here by a factor of 0.1, and in another orthogonal direction it will stretch it by a factor of 10. And all linear mappings do this. And it's kind of magical that you do some linear distortion of the space and then it always does this. You can always find these in three-dimension orthogonal eigenvectors, and in these directions it will either stretch it or squish it. And this by itself is already interesting, that linear mappings do nothing else. And the other interesting thing is that you can use it to reduce the dimension. Let's say in one of the dimension it squishes it by some factor, then you just squish it completely and you leave out that dimension. That's what dimension reduction does. Let's just look at the dimension where a lot of things happen, where you stretch it by a factor of 10 or so. That's where the most action is, and all the other dimensions you just ignore them. And actually, here's one, okay, this A and X should be blue. Here's one calculation, I could talk a lot about this, where you can actually see this. So linear mappings, they do something. You can apply them to the vector. Very often in physics, for example, also in other sciences, this can be a process. You map something to a vector, you get a new vector, and you can do this repeatedly, which means you get a power of the matrix. So let's just assume we have the eigenvector decomposition. So this is the eigen decomposition, which means U is orthonormal, right? So this is orthonormal. Oh, sorry. This should be written again. Orthonormal and pen. And the S is a diagonal matrix. Orthonormal and S is diagonal. And now let's do A squared. What's A squared? So it's just A times A. It's U times S times ut times u times s times ut. Now you have this linear algebra magic, and this here is just, because this is just the identity matrix, which means what you get is u times s squared times ut. And s looks maybe something like this. For, let's say, let me just draw it in 2 dimensions. It would be the same in many dimensions. You have something across the diagonal. How does the square of a diagonal matrix look like? Yeah, just the square. It's very easy to square a diagonal matrix, right? So you just get this, the lambda 2 square, and here you have zeros. So that's very easy. And it's also very easy to see what happens when you take this to the kth power. Now you just have, I think, let me not write it there. Let me write it to the right of this. It's so ak, a to the power of k, is just u times s to the power of k times u transpose, which means s to the power of k is lambda 1 to the power of k, and here I have lambda 2 to the power of k. And what happens if you now, let's say you would normalize this matrix, and again, this is a bit, let me write this lambda 1 again. If you, I'm not doing the full math here, if now k becomes very large and then you normalize this again, and let's say this one is the larger one and this is the smaller one, then the difference becomes emphasized. That's easy to see, right? Let's say this is 10 and this is, even if this is 10 and this is 1, then this grows incredibly more than this one, which means this one becomes emphasized and this one becomes de-emphasized. And it even happens when this is 10 and this is 9.9, right? If you take powers of it, the gap between them becomes huge, which means in the limit, and I won't write this down, only this one remains, which means in the limit, if you apply this mapping again and again, everything will go in the direction of the first eigenvector. Just by so the first eigenvector has a very, very special meaning. Everything will go in the direction of the first eigenvector, magically. And that happens in a lot of processes. You just apply something again, you let the process run for some time, and then what happens is dominated by the first eigenvector, by this strange theoretical concept, and then it gets a very practical meaning. I could talk so much more about this. There are, of course, also YouTube videos. Let me point, 3 blue, 1 brown. Who knows this channel, this YouTube channel? Many of you know it. That's very good because it's a very sophisticated channel with beautifully made videos by Grant Sanderson on many math topics. They give nice glimpses of intuition. For example, here is one about eigenvector, which show you how, and you have nice visualization of the space. We don't look at it together now. But here's a very important warning. I give it at least once in every lecture. Learning from videos, you don't learn anything from videos. It's even for the intuition, these videos are great. They are beautifully made, but it's very, very dangerous. They can be very entertaining. It may appear like you listen to it and you say, now I understood eigenvectors. Yeah? You listen to it because everything is so nice and you understand it, similar to some of our lectures here, maybe, but you only really understand it by doing it yourself. And a simple yardstick is look at one of these videos after a month, you don't do anything with it, you will just have forgotten it. You won't remember, because if you don't do it yourself, it's not anchored, you forget, and you never really understood it in the first place. So it's super deceptive. And I think there's huge danger because there's so many videos now for school, for everything. You watch the videos and you have the feeling, now I understood it. You only understand it by doing it yourself, absolutely. The only good thing is, let me get some additional, and even the intuition. If you feel you get some intuition, then you also have to deepen it yourself. This is so important, this is so dangerous. About exactly the point I made, there's a very nice, here's a link to a YouTube video scene. Who knows the movie A Serious Man by the Coen brothers? Okay, who knows the Coen brothers? Who knows movies? Okay, at least someone. Movies by the Coen brothers, there are a lot of them. Fargo, I think, is, who knows Fargo, the movie or the television series? Okay, yeah, okay, that was the first 10 minutes, maybe 12 minutes today. Let's talk about, there was one more thing. I wanted to show you LSI demo very quickly. Here's and I always like to show this because it's a student project which was done in my group 20 years ago. It was written in OCaml, obscure language, and it still runs today. These guys, they wrote a Windows installer without change. Still runs today. They wrote it in OCaml because they wanted to prove to me that OCaml is as efficient as C++. They lost that bet, but everything else was great. And they agreed that they lost it, but so it wasn't as efficient, but they wrote a UI and everything in OCaml, which is amazing. It's a functional language. This is a movie data set. We have worked with movie data set. You will also get one for this exercise sheet again. So here it's a matrix which you have in latent semantic indexing. This is a variant of the method, probabilistic latent semantic indexing. And I just want to show you, just by doing a matrix decomposition, here I just take movie descriptions, similar as for this exercise sheet for this week, and let's just find 20 concepts by reducing it to dimension 20. And here we can see the concepts, and what you see here. So this, for example, is such a vector, and it's sorted by, so just remember the two vectors B1 and B2 from the last lecture, and let's just look at the entries with the largest numbers. So here you have murder, supernatural, child, occult, robbery, ghost, revenge, death. Okay, that looks, and let's just look, now we can say, let's look at documents which are similar to this concept, and we see, okay, a lot of horror movies, also some fantasy movies, and so on. Okay, of course we also see the usual dirty stuff, relationship, father, son, mother, daughter, brother, sister, and so on. Let's look at the movies here, documentaries, actions, and so on. But the point is, here we have war history, World War II, Nazi France. So this is probably documentaries. We get a lot of documentaries. And just so that it's clear again, this was a completely unsupervised method, right? You just give it the text as a term document matrix and let it figure out 20 concepts by itself, and it will find very meaningful things. We can make this downloadable. There are also other text collections here. It's just, yes, I really want to quit. So that was just, because the last exercise sheet was theoretical, I at least wanted to show you once how it looks like in practice. So today we talk about classification. Classification, now you have objects and classes, and you want to predict for each object the class. And let's just start with an example. So you have a training set and a test set. In the training set you are told for each document what the class is. For example, in a small island off the American coast, the Watleys live in an old mill where a mysterious bloody being. So what comedy, science fiction? No, it's a horror movie. Yeah, so you see, you can get an idea from a starship crew in the 23rd century goes to investigate the silence of a distant planet's colony. Which of the 5 genres? Comedy. Okay, it's science fiction. 2 hearing protection product sales reps have mixed fortune in the exercises of their trades. They first have to. That's not so obvious, right? Some are more obvious than others, because just from the words and from the flow, mysterious bloody being, it's probably not a documentary. Could be. Okay, so now you get these, you can learn from these, you get a lot of these, you can learn from these, and of course the computer doesn't know, these are just letters and words, doesn't know what they mean. And now you get this one. Professor Iris discovers a secret in an ancient stone, and when he opens the crypt, he revives. Okay, what's this? Western. What's this class? You have to predict it from just the words, given the training. That's the problem we are going to. I will show you how to solve it theoretically, and then you will implement it using naive Bayes and see how that goes. And this was the real example, which you also use in the exercise sheet for showing the stuff. I will work with an artificial example, which looks like this. Not so interesting, but easier to work with. So these are my documents, and understand how it's meant. This is a document with 3 words, so the letters here are the words. I could have put spaces in between, but I didn't. This is a document with 3 words, and 1 word is A, B, A. I can have the same word twice, right? And these are the classes, so I have here 6 documents. This gets class A, this gets class B, A, B, and so on. I can learn from these 6, and now I get a new document, A, B, A, B, A, B, A, which class? B, A, which class? And this is also good because this lets you see the problem a little bit more from perspective of the computer, right? Because for the computer, this is as real or abstract as this one, right? Because it doesn't understand what the words mean. And this is not so clear, right? What's now the right class if you have a lot of A's? Does the A documents have more A's or the B? So, before we go into the algorithm, let's briefly discuss the differences to what we already saw. So, one thing is clustering. We didn't do, I did it in an earlier, many years ago, I also did clustering in the lecture. K-means, for example, is a clustering algorithm where you have your objects and you divide everything into clustering. This is sort of clustering what we are doing, but not quite. Soft clustering is what we did in latent semantic indexing. That's actually soft clustering in the sense you have these think of the last lecture with B1 and B2, these concepts, and now every document can be a mix of the concepts. Like, this is mostly B1, mostly B2, this is half B1, half B2. This is called soft clustering. You can belong to different clusters, to different proportions. So, and what's the difference to what we are doing here? So here we are not... Yeah, in clustering it's usually unsupervised, and so you have no learning phase. Today we are doing something with learning. And in clustering you don't have names. You just say, here's my data, cluster it in 10 clusters, please. Here we have names, right? We give the things names, labels. In clustering you don't have that. You just say, please divide it into 5 clusters, whatever they are. Yeah. LSI, no learning here, and today we are doing something with learning. We are having a training phase and then a prediction phase. Let's also, you need this for the exercise sheet, very quickly talk about quality evaluation, and maybe just consider this example again. Now you did this, you learned, you trained here, and now you have a lot of documents to predict. And let me maybe also show you the real data set for once. So, yeah. Let's look at the test data set maybe, and it just looks like this. Yeah, so it's just the first, it's tab separated values, 1 record per line. The first column is just the genre, so this is comedy. And of course for the test set, this is not what you should use, but just test, this is what you use. A shy San Francisco librarian and bumbling falling. And now you should predict what it is. And sometimes you're right, sometimes you're wrong. And let's maybe also just look at the distribution of these things. Maybe for the training set here, if I just cut the first column, I just get this. Let's maybe sort this and count the size of each group with unique minus C. So you see it's an uneven distribution. We have over 10,000 comedy plots, documentary, horror, science fiction is the rarest, which corresponds to IMDb data. So we took a sample, not too many, so that you don't have problems efficiency-wise. So when you do the quality evaluation, you will predict sets, which means, for example, for class comedy, you have the documents, the movie plots, which are really comedy, and then you have the documents which you predict as comedy. Ideally, they are the same, right? Let me draw a picture. I mean, this is, for example, for comedy, this is the set of movies which are really comedy, and this is the set of movies which you predict as comedy. Hopefully they are very similar, but yeah, there's a part which you don't get. These are comedy, but you don't predict them, and there are some which you predict as comedy, but which are something else. So what do? We can compute for each class precision and recall. I will not talk about it too much here. I don't think I will talk about it at all. You can just read off the formulas and work with it. Maybe just one thing, so you have precision and recall, 2 numbers, and they just measure somehow the overlap. And then you have the F1 measure, also called F1 score, which turns this into 1 number. And why does one take the F1 measure? Well, let me just, if you take the average of the reciprocals of these, so if you take this, no, let me not write it with parentheses, divided by 2. So if I take this, if I multiply this by P times R in the numerator and denominator, what I get is P plus R times 2P times R, which is just 1 over F1. Which means F1 is just, you just take the average of the reciprocals and then the reciprocal again. So that's called the harmonic mean. Right? The mean would just be P plus R over 2, but for F1 you take the harmonic mean, which means you take the... But that's just why this formula looks maybe a bit strange. It's actually quite natural. This also might be an exam question, or at least sometimes I have it in the exam. This is one of these many little proofs. This single number is exactly 100% or 1 if both of these are 100%. This is the only way it can be 100%. So it's a good single measure. You will evaluate it for the, just to get, then you get for each class a number which tells you how well you are doing with respect to that class. One more thing before we dive into the algorithm. What's the difference to what we did in lecture 2? We had quality evaluation, precision at K, average precision, discounted cumulative gain, bpref. Well, the setting there was, the ground truth was a set. You have a query, and here are my relevant documents, but what you compute was a ranked list, right? When you have a ranked list and your ground truth is a set, then these measures from lecture 2 are the right measure. What we have today is the ground truth is a set, all comedy movies, and what you predict is also a set. Here's everything I recognized as comedy movies. And in that case, you use precision recall and F1. And here's a comment which you may not fully understand now, but as you work on the sheet and later, very often you find papers or also master thesis where you get a table and then it just says here is precision and recall and F1. So if you say precision recall F1, you always have to say what are these two sets, otherwise one cannot understand what you're doing. It's always with respect to two sets, right? You have the ground truth set and what you predict. That's what the red comment is about. Is there any question? This was just some basic stuff, setting the scene. Yes, please?
So in the clustering, we have hard and soft clustering. Do we have something similar in classification? Or do you always classify to one thing?
No, actually we have exactly the same thing, and it will be apparent today. You will always have a soft score. I mean, you can always turn soft into hard by just taking the largest one, right? And that's what we will do today. So naive Bayes will also give you with probability so-and-so it's this, so-and-so it's this. You can just leave it there, and in all of deep learning you also have this. You always get these scores, and now you can either say, okay, take the largest one, then it's hard, or leave it soft. So very good question. You basically always have that distinction. Are there any other questions or comments? So, naive Bayes is based on probabilistic assumptions. So, and for that you should understand two things, which you should have heard before at some point, kindergarten, school maybe, maximum likelihood estimation, and conditional probabilities, or Bayes theorem. Very, very basic fundamental stuff, maybe a bit rusty. So I will give you a crash course as usual. So maximum likelihood estimation. That's just to understand what this is. A very simple example. Coin flips, head or tails. Somebody has flipped the coin 20 times, each flip independent from all others. 5 times head, 15 times tail. And now I have to say, well, is this a fair coin, or more specifically, which probability distribution over head and tails is the most likely? Okay, this, I mean, there's 5 times age, 50. If you would have to guess, you would probably say this, right? It doesn't look like a fair coin. With a fair coin, I would expect 10-10, but it's 5-15, so it looks like tail is 3 times more likely than head. But it looks like this, but is it like this? In which sense are they the most likely? And this you can do mathematically, and let's just do this. So what's the, and I don't have anything else here, so I can start writing here. So let's just, take P, let me write it like this. Oh no, let me not even write it like this. Let me just So P is probability of heads, and then probability of tails is just 1 minus P, right? I just have 1 degree of freedom here because it's always a probability distribution. So then probability of tails is 1 minus P, and I want to find the best P. It's again sheaf. Okay, so what's the probability of this sequence? H, H, T, T, and so on. The sequence above. In terms of P. So what's the probability of seeing exactly this sequence, if P is the probability of heads? Yes?
I think it should be that we take the probability of H, that means P, the power of the times that H occurs.
Which is?
5.
Yeah, P to the power of 5, that's good.
Times 1 minus P to the power of that's 15 times.
Yeah, 15, and that's correct. So combinatorics is, in a nutshell, is figuring out where to multiply, where to take to the power, and where to plus. So if you don't know combinatorics, then you're 5p, p to the 5, p plus 5, p to the 5 plus. But that's correct, yeah. You're multiplying the probabilities, 20 probabilities here which you multiply, and 5 times it's p. Yeah, that's correct. And so now we want to find P such that, and let's just call this star, is maximized. That's what maximum likelihood estimation is. And that's a whole mathematical field and also practical field. You have something, you observe something, you have underlying probabilities. When is this observation the most likely? That's maximum likelihood estimation. Find the parameters such that the thing I observe is the most likely. Okay. First thing we do, equivalently, and we have already seen this, that's this. Equivalently, find P such that, and I don't maximize this because now I want to compute derivatives, and derivatives P to the power of 5 times, that's not so nice. Let me just take the logarithm of this, such that f of P ln of this is, let me just write it like this and simplify it in a second. 1 minus P over 15 is maximized, yeah? And this is same. Let me just write it very briefly, because log is a monotone function. Because ln is a monotone function, right? Whether I maximize, where this is maximized, also the original one is maximized. That's easy to prove, and we don't prove it now. We have already used this before. Okay, and now you see why in all of deep learning and whenever these things, you always take the log, because this is much easier to handle. And that's not the only reason we use the log. F of P ln, and this is, logarithms law, you should know them by now. That's f times ln p. So this now becomes a product, so the power becomes a constant factor, much nicer. The product here becomes a plus 15 times ln 1 minus p. Okay, let's take the derivative. F prime p is, what's the derivative here of ln 1, not 1 minus p, but p. 5 over p, that's why we take the ln, because it has a particularly nice derivative. And here we have 1 over 1 minus p, inner derivative minus, so it's 15 minus 15 times 1 over mine. Yeah? Okay. And now we want to find p where this is 0, where the derivative is 0. So this is again one of these simple calculations which one cannot practice enough. So we have f prime of p equals 0. Let's write equivalence here. That's equivalent to saying 5 over p is 15 over 1 minus p. And this is let's not take p equals to 0 or p equals to 1, because if p is equal to 0 or p is equal to 1, then this thing, we have a problem here, right? Then we have ln of 0, which is the lim for p equals to 0 of f of p is what? If p is 0, where does this go? Minus infinity. It's ln 0, it's minus infinity. And for when p goes to 1, where does it go? Same, yeah, exactly. It's also very typical. This p times 1 minus p, it's kind of symmetric. Not exactly symmetric, but similar things happening on both ends. So we don't look at these. We want to find a maximum value. So if we find something larger than 0 here, which we will, it will be larger than minus infinity. So let's not bother with the borders. So here we can just take now, if p is not 1 or 1 minus p, then it's really equivalent. So we take 5, 1 minus p is equal to 15p. And this is this correct? 5 minus, and this is equivalent to, now it's really equivalent what I'm doing. Now equivalent to 5p, 5 is equal to 20p. And you can already spot the solution for, which is equivalent to 1 over 4, which is exactly what we assumed in the first place. So the only 0 of f prime is 1 over 4, and one should also check that the second derivative, we don't do that here, but you can easily do it. You can also compute the second derivative here at 1 over 4. It will be negative, which means we have a maximum at p equals 1 over 4, which is what we wanted to prove. Yeah, so this function, so this was simple but also not trivial, and this was just one variable. Now imagine this with several variables, like you don't have head or tails, but maybe you have a die which you roll 6 possibilities. Now you have 5 degrees of freedom, or you have 6 probabilities which together sum to 1. Then this becomes again Lagrangian optimization, which crops up a lot in these contexts, which you have also seen. Okay, so that's maximum likelihood. Yeah?
Strictly monotone for the ln. I think we need that ln is strictly monotone, because the zero function wouldn't work.
Very good. It's true. This is very true. It has to be a strictly monotone function, yes, because otherwise you're making things equal, which in the original one. Yes, very good. Strictly. Which ln is, right? Let's just, so that everybody, no, this is, I need more space at the bottom. ln looks like this, ln x, and this is 1. Okay, any more questions or comments before we go to the next mini probability crash course? And the next one is conditional probabilities. That's also, I know people have trouble with this, but actually it's very easy, and it's always good when you want to understand a basic concept to look at a simple non-trivial example, which I will do now, and then try to understand it for that example and work your way up from there, like computing 2-digit numbers in your head. Start with the simple stuff, then work your way up from there. So let's assume we have a probability space and 2 events. Let me just ignore this for a second. Let's just start with an example right away, and then let's see what's written on the slide. So, so our random experiment, there's nothing here. So the random experiment is, and that's always a good one, is roll a die. Roll a die once. It's just once. Which means our omega, and that's also, you don't understand probability theory as if you always be clear about what's my omega, what's the space of possible things that can happen. And you have to give these names. Here we just give these the natural names, which is just the numbers 1, 2, 3, 4, 5, 6. And that's also such a basic thing about math. When people have problems with math, it's often because basic concepts are not clear. Probability, and then it's not clear in your mind, and when it's not clear, you can't compute. It's like when you program a computer, you have to be very specific. So the probability space is a set, the set of possible elementary outcomes. And each of these, so for each x in omega, p, probability of x is 1/6. So that's a particularly simple example. It doesn't have to be equiprobable. Here it's equiprobable. Now let's look at 2 events. And an event is a subset of omega. An event is a subset of omega. Let's look at this event, and you can also give events names, but it's not important. This is the event even number. Yeah, the event, I'm sorry, that an even number is rolled, which means 2, 4, or 6. An event is just a subset of omega. Even number. And let's look at another event, b, which is another subset, and that's just small number. Yeah, so this is also a subset of omega. Could be the whole set, so that's a small number. I roll a small number, namely less or equal 3. And now let's talk about, before we talk about conditional probabilities, let's just talk about normal probabilities. What's the probability of A? Now, what a probability is just if you have these elementary events and they are all equally likely, then it's just the size of A, so you just do counting. So in this simple setting, and eventually all of probability reduces to this simple setting, it's just combinatorics. It's just counting how many things do I have in my whole set, how many things do I have in my event. So this is just, I know this is very basic, but I think this is good for many of you. So that's just this. And the same thing for probability of B. Yeah, if the problem becomes more complex, immediately people struggle, and the only reason they struggle is because it's not clear what they have to compute. As soon as you ask yourself, what's the omega, what are my events, what are the subsets, then you're back to counting, and then maybe you have a counting problem, maybe not, but then at least you are on a level where you can make progress. So this is this relative size of B, which in this case, it's also 3/6, it's 1/2. And now, in this context, you can understand very easily what a conditional probability is. So A given B. So what does this mean? Now I can say very easily so after this vertical bar, we have what is given, which means we have 1, 2, or 3. This is given. We are already in a smaller space now. It's 1, 2, or 3. Now, what's the probability that A occurs? So what would you say? We are in the space where only 1, 2, and 3 are possible. So what's the probability that also A occurs? And maybe before I ask you, let me write down the definition of this. Now I only look at the part of A that's actually in B, because I'm already in B world now, right? So I take A intersect B, and it's very natural to define it that way, because my probability space is now only the B's. And now I take the relative size over all B's. So my B, I have 3 things in B, and now I just have to look of these 3 things, how many are in A? How many are in A? Yeah, just 1. So it's just 1 over 3. That's just 1 over 3. But this is also, and this is, what is A? Let me just do a transformation, and then I prove Bayes' theorem for this simple setting, but the general proof is not more complicated. I can just divide by omega, both in the numerator and the denominator. So this is B divided by omega. I don't write a double fraction here. And what is this? This is the fraction of omega of this. This is just by definition the probability of A intersect B divided by the probability of B. Yeah? And actually, I haven't written this here. The probability of A intersect B is, what's the probability? It's the size of A intersect B divided by omega, and which is, A intersect B is just one element, right? It's 1 over 6. So this would also work. I mean, obviously, that's 1 over 6 divided by 1 over 2, which is also 1 over 3. And maybe, let's do, there's also sometimes the Bayes' theorem is sometimes formulated like 2 here. So from this, let me just put it up here. I mean, what this says, what I've proven here is probability of A intersect B is, if I just bring the denominator to the other side, then it's just the probability of A condition B times the probability of B. But since A intersect B and B intersect A is the same thing, I mean, this is exactly the same thing, I can also reverse the roles of A and B here, right? It's this, it must be the same as this by the same logic, which means these two are the same, and that's Bayes' theorem. So it's actually, it looks like, okay, what is this? How is it proven? It's this very basic, you are in a constrained space. Actually, the most fundamental math in the universe is always like this. If you boil it down, Heisenberg's inequality is also something as simple. The most basic laws of nature are like super simple math if you just start from basic things. And just if you look at it from the abstract, they look maybe scary or not. Any questions about this, conditional probabilities? We will use them in the following. Okay, so let's start. So this is the second part of the lecture. Let's maybe start a little bit and then have a break and then we continue. So that's just these 13 slides left. Naive Bayes makes some now we want to, this is our setting now. We want to, we have such, here's the training data. This is what we are given. We want to learn from this text with labels. So now what we assume is, we assume some underlying probability distribution, right? It might not be there, we just assume it. It's an assumption, which means it's wrong. We just assume it so that we can do mathematics. And then we just do the mathematics whether our assumptions are correct or not. We also did this with latent semantic indexing. When we used the Frobenius norm, we made some implicit assumptions. They are not right, but still something useful comes out. We assume that we have a probability distribution over the classes. Some classes are more likely than others, and we will try to estimate this. We will see this in a second. For each class, we are assuming a probability distribution over the words. So maybe for horror, bloody, spurt, splatter, I don't know what, will be more likely than other words. So we have a probability distribution over the words. And now we assume that documents are generated by the following process, and you will see how that assumption comes into play in a minute or after the break. You have a question now? WC, yes?
Yes, and is it the probability of what probability exactly is it that the word occurs under the class, or I think it's another?
I think this will, it's not clear right now. I mean, first, this is just a probability distribution over words for a particular class. And every class has a different distribution. And now I will explain how we use that probability distribution. That I will explain now. Namely, to generate a document, I want to generate a document. First, I pick a class according to this probability distribution over classes. Let's say it's equidistributed. We have 5 genres, and I pick comedy with probability 1/5. And now I pick one word after the other, independent of the other words, and I pick each word according to this probability distribution. So I just say, let me pick the first word. And I just pick it with this probability distribution. And now I've already picked class horror, so now I will pick the word blood, spurt, splatter, more likely than some other word. And now I do this one after the other. And what I haven't said here, and I'm wondering myself right now, is when I stop, let's just ignore that for a second. The length of the document, I think, is just fixed. This is not part of the model, so I'm just saying generated. Let's talk about this later if it becomes an issue. I have a document of length 12. Now I want 12 words, and each word I generate independently of the others according to that probability distribution. And I really want to understand how unrealistic that model is. This means I could now generate blood, 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 or and the blah. In two ways, this is super unrealistic. One is words are not independent, right? When I have science documents and I have chosen relativity, then probably theory will be more likely. I mean, it's not just, this is also called bag of words, this model, where you just have independent words, but in reality they form sentences, they're dependent from each other. And also you have word order, right? I mean, a normal sentence, you can't just perturb the words or sort them lexicographically, then it's not a sentence anymore. So super unrealistic model, but that's very typical in all of learning. You have these super unrealistic assumptions, but at least you have something to work with and you can do the math, and then you just do it and hope for the best. Is there any question about this simple model? And that's why it's called naive. Why it's called Bayes, we will see in a second, but it's certainly naive. Yes, please?
Still not sure is now P, W, C, and P of V intersected C, or how to translate it into...
We will have an example in a second, and then it will become super clear.
Okay.
we have an example where you just see all these probabilities. I could now give you another example, but then I would just repeat what you will see in a second. Yeah. So maybe if it's not clear, the example will help you. And and let's maybe do the example and then the break. That's maybe then a good way to have a break. So, yeah, we have a number of things now. In training, I can just count. Let's just look at this one here. I just count how often do I have comedy, how often do I have romance. I call that TC. This is now combinatorics counting. And now I do another count. In all documents that I comedy, how often does the word Punjabi occur? You can just count it, right? Maybe it occurs 3 times in comedy plots. And then I count how many words do all documents from class comedy have altogether. I count this. And now I just do the following. This is quite natural. So my probability for a class, I estimate it like this. So maybe I have 10,000 movies, 4,000 are comedies, then my P comedy is 0.4. Yeah? And it's not equidistributed on purpose here. And also this probability, so maybe I have all the comedy movies have 1,000 words and just one of them is Punjabi, then its probability is 0.1% for Punjabi. And maybe 10 of them are movies, then 1% probability for movie. And actually these are, that I take these, this is exactly maximum likelihood. So if I don't know anything, then this is like this is exactly what I did with the head-tails thing. This is the most likely underlying distribution to generate what I saw. So these are the most likely probabilities then to generate what I see. And we can just compute these numbers. And this is just a forward pointer to later. These, of course, can easily be 0, right? Maybe blood never occurs in a comedy movie. Then the probability blood comedy, P blood comedy would be 0, or N would be 0. And we see about that. And now let's do the example. And after the example, we have a break. We now do the training of naive Bayes for this example. And the first thing we do, let's just see, we just count how many documents of class A do I have? How many documents with class A? You tell me all the numbers, 3, yes. How many documents of class B do I have? I also have 3. Yeah. And so how do I, which means, do I have a variable for this? No. Oh yeah, I call it, training set T of objects. Okay, I gave it a name, which means I have T objects in total, which means I take a probability for A. It's super simple if you write it down like this. Yeah, they are just 1/2, both of them, right? P of B is just, these are maximum likelihood estimates. So in my model, I just take these to be 1/2. Now I count, and that's your question, and I hope it becomes absolutely clear now. So I have 2 words, only 2 words, my vocabulary is A or B. The number of A's in documents of class A. So I just look at all the documents of class A, there are 3 of them, and I just count how many A's do I have. How many A's do I have? 10. I think that's correct. 10. And let's also count the number of B's in A. How many B's do I have in document of class A? 5. 8. Should we take the average or harmonic mean? Maybe geometric mean? I think it's 5, right? Just so that we are all on the same page. In A, it's this one, this one, this one, this one, this one. And you see the order doesn't matter. It doesn't even matter in which document they occur. Very strange thing we are doing. And then we had another number, which is just how many words overall are in document in class A. How many? How many words are in A? Yeah, 15. It's just the sum, right? So, and I can use these to estimate my... So this is now the probability of A in A. So this is my PWC. Capital letter here is the class. This is the word. And this is just by a maximum likelihood estimate. It's just the proportion of this word over all words, which is just 2/3. And the probability of B in A is just NBA over NA, which is 1/3. Yeah, I just have two words, A and B, and my probabilities, they have to sum to 1. 2/3 of the words in documents of class A are A, 1/3 of the words are B. Simple enough. Let's do the same thing for class B. How many A's do I have in documents of class B? 1, 2, 3, 4, 6. I think you are correct. How many B's do I have in documents of class B? 12. Wow, what a coincidence. NB, how many all in all? 18, the sum of them. And now let's compute the probabilities again. Let's be less generous with the space here. What's B, A in class B? P of A in class B is just the proportion of N of A in class B of all in class B. So it's 1/3. So 1/3 of the words in documents of class B are A's, and then the rest must be 2/3, right? So P of B is just NBB. One has to concentrate here so as not to make a mistake, and that's just 2/3. So, and just to summarize, and then I will also summarize it in, so the result of the training . The result of the training, we have learned 6 numbers. So we have learned the distribution over the classes. The rest was just intermediate. We don't care about the n's anymore. We have a probability over classes, and for each class we have a probability distribution over the words. So we have P AA. For class A, we have this probability distribution. 2/3 are small a's, and 1/3 are small b's. And for class B, it's exactly the other way around. A, B, it's 1/3, and P, B, B is 1/3. And I hope it's absolutely clear that you can do the exact same thing. Oh yeah, this is can't be right. I started talking too early. I hope it's clear that you can do the exact same thing if you have 17 classes and 500 words. That nothing is different. This was just to keep it small. So that's the result of the training. You just computed from numbers. That you take these portions was just maximum likely principles. If you just have the numbers, this is the most likely distribution to assume. We haven't used Bayes' theorem yet. Is there any question about this before we go into the break? Or you think about questions in the break? So, 5-minute break. We are back online again. 2 degrees colder. Okay, and here's the T missing, training. So we were talking about naive Bayes. We did the training. The result of our training was just 6 numbers. Did any question occur to you on the training process and on these numbers? So we just both classes equally frequent and hence equally likely. In the A documents we have 2/3 A, 1/3 B's. In the B documents, capital B documents, the other way around. Simple enough. And the same you will have with words and genres for the exercise sheet. Now we do prediction. Now, if we have learned these 6 numbers, how do we do prediction? And now comes the base part of naive. We have already talked about the naive part. We want to compute this. We're given a document. So conditional probabilities, you can understand it as the right side you are given, the left side you want. That's not quite correct, but that's a first approximation. We are given a document, D, what's the most likely class? Now we can do Bayes' theorem. We can just turn this around. Let's maybe, I think it pays to just, so what we had was, so we have A. You can always derive Bayes' theorem yourself. You don't even have to remember it. I don't remember it. I always derive it myself like this. You can say A under the condition B times probability of B, or you can do it the other way around, like B under the condition of A times the probability of the condition. So this way or that way around. And what that means is that you can, if you just, if you have the one thing, or you want the one thing, probability of A under the condition of B, you get it from the other thing by doing, just bringing it to the other side. Probability of A divided by the probability of B. And if you wonder about whether it's this way or the other way around, just derive it from first principles again. So that's what we're using it. We want it this way around. Yeah, given a document, what's the class? What we know from a training, or what you will see in a second that we can derive it from a training, given a class, what's the probability for that document? These were our assumptions, right? They were in the direction, I have a class, now generate a document. So this is more like what we are given, and here we have these probabilities, probability of a class, we have learned those, and this thing, we have no idea what it is, but we will see in a second that it doesn't matter. Now what's this? Probability that the document of seeing that document means it's the probability that the first word is the first word. So now we are asking ourselves, what's the probability of this, of seeing this? And the probability is, it's the probability that the first word is comedy. That's just the probability of comedy for class comedy times the probability of movie for class comedy times the probability of is for class comedy, and so on. So we just multiply these, and let me just, so here this is a pi, but this is nothing else than we have, so this is P, yeah, that's now the probability of word 1 for class C times the probability of word 2 for class C. Of course, W1 and W2 could be the same, right? You could have a word repeated here. It's just the product of these probabilities. It's just what we, yeah. No, it's not what we did for the example yet. I will show it to you in a second. So that's just the probability of seeing that document is just the product of these word probabilities. And then I need to add this. So this was just this part. This was just this part here. And then I have to add this. This happens on the next slide. So we have the probability which we are actually interested in is the product of the word probability for that document times this divided by this. So it's the product of these word probabilities for the words we have in the document times the probability of the class divided by the probability of the whole probability of seeing the document independent of a class. Now, I will come back to that later. Ignore that note for now. It's just for reference. This here is the same for all classes. We don't know how to compute it, but we don't have to compute it because in the end we just want to find the class where this is the largest. So if there's always times 0.3547 for each of them, we can just ignore it. It's similar to the monotone finding the maximum. We just want to find the maximum class in the end. So we will just ignore this, which means we will just compute this thing, which is in bold here for every class, and then pick the one where it's largest. And we will just do that for an example now. So, and you will see how easy it is when we learned. What did we learn? Let me write it down again. We learned during training. These probabilities, PA 1/2, let me write them down again. This I think was 2/3, I hope so, right? I had this thing, this was 2/3. This was 1/3. It's now for the third time that I'm writing them down, and I think for the last time in this lecture. This is what we learned. And now we use it to predict. So now we want the probability of class A for the document AAB. And my notation is not 100% consistent here. I'm not writing class is equal to this. I'm just writing what I observe. So what's the probability of class A for the document AAB? And given by the formula on the previous slide, this is, I can just turn it around. I just take the probability of this document given class A, and this is something I can compute, times the probability for the class A divided by the probability which I cannot compute, which means the overall probability of seeing that document. And this probability AAB, this I can break down. This is the probability of word A for class A times this probability again times P of B for class A. You see there's no problems with repetitions here. And actually you see a nice thing, which I will come back to later. If I have a word here 5 times, I will have that probability to the power of 5. And the 5 is just the term frequency, right? So the term frequency will appear as a power here, if I would write it that way. Times, and this is the probability for class A, times this probability which we do not know and do not have to know. And let's plug in the numbers. So that's now 2/3 times 2/3 times 1/3 times 1/2 divided by the mysterious probability, which we don't know. And now we do the same thing for class B. A, B. And this is the probability of, now we turn it around. What's the probability of seeing this document? And it's the same document for class B, multiplied by the probability of class B divided by the mysterious AAB probability. And this is now, and now we break, and this is base, right? Here we use base. Maybe I should write it. So this is using Bayes' theorem, and we're also using it here. No, that's not true, what I said here. I think I should be more careful. Maybe I should do it like this. So this is using Bayes' theorem. And this here is using the independence assumption, right? Dependence assumption from naive Bayes. Naive Bayes. Yeah. So in a sense, you could say this is the Bayes and this is the naive, right? I could have also written it that way. The first one is the Bayes and the second one is the naive of naive Bayes. Okay, and now I compute and I do the same thing here, but now it's relative to class B. PA times P A of class B times P B of class B times probability of class B divided by the mysterious probability. And if I compute this, now I get 1 over 3 times 1 over 3 times 2 over 3 times 1 over half divided by a last time this mysterious probability. So now I don't have the exact numbers, but I do have relative numbers. So what I can compute now, and let me do that at the top. What I can compute now is I compute the odds ratio. I can compute the quotient of the two, for example. Let's take the quotient of this, the A probability that it's class A divided by the B probability. And the nice thing is if I take I would just want to know which one is larger, so I want to see, do I get the number larger one, smaller one, or 1? Then 1, it's a tie. If I divide them, then this strange probability, which I don't know, just falls away, it cancels out. And what do I get? Let's even write it down very explicitly. So I get here 2/3 times 2/3 times 1/3 times 1/2, and here I get 1/3 times 1/3. So it doesn't, you don't even have to compute them, because most of this cancels out. And the result is 2. 2. Which means, what do I predict? Yeah, I predict A. So, for this document, AAB, I predict A. And actually, if you think a bit deeper, or what? Now, we will come back to this in the next lecture. It's not important for now. What do you think is there a simple way, by just looking at the thing, when it will predict A and when it will predict B? Yeah, that's exactly what it will do. It will just predict A when there are more A's and B when there are more B's, and when they're the same, it will be a tie. And you can actually prove that from these numbers. And it's fairly easy to say. This was not so obvious when we started this, right? But this is what naive Bayes does in this case. And there's also a deeper truth behind this. So, that's naive Bayes. It's as simple as that. This was an example with 2 words, 2 classes. Now you do the same thing with 5 classes and 10,000 words or so. Yes?
Do we all the time ignore the order of the word description, right? We just say if it occurs, it doesn't matter.
Exactly. You see here all these assumptions come into play, right? The order is totally irrelevant. This we could sort all the documents, and yeah, there's also a hint on the exercise sheet about this. Yeah, and you see it here because it's just the numbers multiplied, right? The order, which is totally unrealistic, naive, but still, yeah. Also the deep learning, the models driving ChatGPT. Oh my, I have no power here. Actually, just a paper came out because these transformer deep neural models, they have position somehow encoded, and now someone has proven that you don't need it. You can even ignore the position. The network, the neural network which drive things like ChatGPT, they learn it themselves. You don't have to. You can even give them the stuff in other order. Now, just some, so that's the basic working of naive Bayes, and now come some refinements which are important for the exercise sheet, so you should definitely listen. Maybe before I go to that, let me show you the exercise sheet. Here it is. It's pretty obvious what you should do. You're getting these collections, one for training. And I hope it should be clear that for training, you can, of course, use these. Like in the training, we use these to compute our probabilities and stuff. And when you test it, you just use them to evaluate your algorithm, right? When you test them, then you just get this sentence here, and then you're supposed to predict this, and you just use the true label to evaluate how well you did. And so what you should do, you should write code which does the training, which computes these numbers, the class distribution, the word distribution. You write a method predict, which does the prediction, as we just did for the simple example. And then you write a method to evaluate it. And what you should also do is output the words with the highest probabilities, because that should give you an idea of how well the method did. So it's train, predict, evaluate. And then you should just run your code on the data. That's exercise 4, and then there's again a table. Okay, and here are some important refinements. They are so important that if you don't do it, it won't work. They are very important. So one thing is, when you see a lot of probabilities being multiplied, there are 2 things, and that's universal, which can go wrong, or which are a problem. One is, you have 1,000 probabilities here, one of them is 0, everything is 0. Is that a problem? Yes, that's a problem. I mean, think about it. I mean, yeah, your comedy class, I said it earlier, maybe blood never occurs in comedy. And now in prediction, you have the word blood, and the prediction for that class will be 0. Even if all other words shout that it's a comedy, just one word will just make your whole probability 0. That's bad. And you need smoothing here. And the way to do smoothing is when you compute these probabilities from the counts, you just add an epsilon. That's a very heuristic method. And let's just briefly understand why you also... So you just add an epsilon, which means you make, by adding the epsilon, now it's strictly positive. And just understand what I write here. Let's just do the math quickly. If I sum these up for a class, so if I sum up over all words n wc plus epsilon, then what I get is the sum over all W of NWC plus the sum over all W times epsilon. And this here is just the number of words in all the documents from class C. We have already seen it, that's just NC. And this is just number of words times epsilon, which is why I have to, this is just epsilon times size of the vocabulary, which is why I have to add it here. If I don't add it here, I don't get a probability distribution, as simple as that. So for the exercise sheet, it's written on the sheet also, just take 0.1. That's one of these hyperparameters which can make huge difference in practice. I mean, if you take it very large, then you smooth out everything, you make everything equal. Communism probably doesn't work. If you make it very, very small, then you are not very far away from the zero case, right? Then again, if a word doesn't occur, the probability is so small that that class gets never predicted. Now, there's another case. So there are these word probabilities. There's also the class probability. This can also be zero. Let's look at that case too. So what about that? What about PC equals 0? Is that a problem? What do you think? What does it mean that in training PC is 0? Yeah?
I think we have to divide by 0 later, and that's
Divide. We don't have to divide, right? Here we just multiply. We're just multiplying. We only divide by a strange probability which we ignore.
I mean, if we have a probability of 0, that means in training data we didn't have any of that class,
Yeah.
and therefore it's hard to predict anything of that class.
Yeah, exactly. It means PC0 means count of that class over all things. P comedy 0 means we didn't see a single comedy plot. If we didn't see a single comedy, how can we predict it? We know nothing about it. So in that case, it makes sense, right? We didn't see it ever. So, and that's written on the slide. So we didn't see it, and so it's actually meaningful. I mean, depending on the application, you could argue, okay, let's sometimes predict comedy even if we never saw it, but I think here it's reasonable to say, okay, if we never saw it, how can we predict it? We never predict it. We should ensure that we see it at least once. So at least for multi-label classification with few labels, that's very reasonable. We expect to see everything a few times at least. Here's another important thing. So I said two things are dangerous when you multiply a lot of probabilities. One is 0. The other one is numerical. If you multiply many probabilities, and think about it, the probability in our toy example are 2/3, but even 2/3, if you multiply it 1,000 times, you get small numbers. But here, now it's probability distribution over a vocabulary with 10,000 words. The probabilities will be something like 0.0001, and you multiply a lot of them. And think about it. So what's the smallest number that you can represent? That's actually a very interesting research topic by itself. What's the smallest number you can represent with an 8-byte double? It's 2 to the minus 1074. It's actually less than 1024, which you would expect because you have an 11-byte mantissa. Maybe let me write that here. I think I have a link below. So that's 11-bit mantissa. If you know how floating points are, so the exponents, you have 11 bits, 1 bit for the sign, which means you have 10 bits now, which means you would expect, and then 2 to the minus 1024, 1024, and then you have a thing called subnormal representation. So you're interested in And that kind of stuff, it's actually super interesting. It's also relevant for stuff where when you're programming low-level C++, it's actually quite important to understand how how numbers are represented in a double. So the IEEE standard has all kinds of fancy stuff. It's a bit like UTF-8, a lot of magic going on there. So you have subnormal representation where you can, so that you can represent smaller numbers than actually the mantissa gives you bits, which means in the end it's, and there's an article I've linked to a Wikipedia article here or in the end. There are also things like you can store infinity, not a number, -0, +0, lots of interesting things. So this is a number which you reach fairly easily. So let's say you have probabilities, they are less than 1 over 10,000. That happens quickly. If you have 10,000 or 100,000 word vocabulary, you multiply 54 of them, which also happens quickly. You have a document of length 54, then product is already 0. So it happens quickly. So what do? You just take the logs. Then your product of probabilities becomes a sum of logarithms. And then the problem goes away. So the logarithm occurs naturally here in another, as a savior in another way. Not only is it easier to derive and stuff, and products become sum, but also some numerical stability problems also disappear. Yeah, and because it's monotone, it's just as good, right? You find the thing with the largest log or the thing with the largest non-log, same thing. And I think your comment should be strictly monotone. That's important also here. If it wouldn't be strictly monotone. And God forbid, don't take, I mean, you could now say, okay, just to compute it, let me take the log, and in the end I take exp again so that I get the real probability. I mean, don't do it, because exp, let's just maybe verify it here. Python 3 minus, let's just write it in import math, print math exp. And now we are talking about small numbers, so minus 700 should still work. Yeah, that's a small number. What do I claim? 46, so 45 should still work. That's still a positive number, but already very small. 746 is already 0, right? And minus 746 is not a large number, so you say, yeah, sure, of course I can take the exponent of that, yeah. You can't. That's of course 0. So don't take, just work only with the logarithms. And there's okay, so this is important, you have to do this, otherwise it won't work. You have to do smoothing, add an epsilon, you have to do logarithms, otherwise things become 0 quickly. Here are a few things which you could do, but you don't have to do. You don't have to take words as features, right? So in my example, you could also take you can do anything. I mean, this is now the problem of what do you take as input features. I could also take the characters as my input features, right? So this here has so many L's, so many O's. I could take the bytes. Maybe there are special characters here. I just take the bytes, I take it as UTF-8 sequence, and I take the bytes. And actually there's a whole research area on this for neural network. How do I feed my text into the neural network? As words, as bytes, as characters, as subwords. There's also where you just break the words into smaller parts, and you feed those smaller parts. That's actually what you do. You do like smaller parts. That works the best. Byte pair encoding, it's called. So you have, so for the exercise sheet, just do it with words, but I just wanted to mention it. You can also add more features, like why not to give a little bit of order. For example, when you have this World War as one feature, the whole phrase. When it occurs next to each other, you do this. You could do it with everything that occurs next to each other, or only with things that frequently occur next to each other, right? You could do that. You can input anything as feature. You could also input as feature that this is the second word of the document. Or whether the second word of the document starts with a capital G or something like this. You could just include stop words like and. These are called stop words. They are frequent words. You could just ignore them. You have a lot of and, in, as. You just do as if they weren't there. Ignore them. You could not count frequencies, but use more fancy scores. So what we did, you just count frequencies. Actually, TF occurred, I mentioned it. Just replace it by TF IDF or something and see what happens. You could do that. For the exercise sheet, you can do it. The only thing you have to use is to use... Oh no, you don't even have to use this for learning, but just to filter out what's shown in the end. In the end, you should show the words with the highest probability for each document. And if you don't filter this, it will be and, the, is. They just, because they are the most frequent. Naturally, they are not very discriminative between the classes, but you don't want to show them, so just filter them out. Everything else and whatever else you can think of to make it better, do it. And here's the last thing, and listen carefully because that's important. Of course, you should implement this with linear algebra operations. And I think I've shown it to you. No, I mean you have done the exercise sheet 2 exercise sheets ago, where actually it was just very few lines of linear algebra where you computed the scores for all documents. And something similar you can do here. In particular, I will show it to you now for predict, like show you the basic idea. You have to figure it out yourself for training. So let's again assume the documents are given as a term document matrix. Why not? And you don't have to write the code. This is actually, if you implement this, the hardest part, and we give it to you as a late Christmas present. So constructing the document term matrix, we just give it to you with TF entries now. You can just proceed from that. And then everything can be done with linear algebra very elegantly. And this is something you should really, if it wasn't clear to you so far, it should be clear to you now. Whenever you have weighted sums, and many weighted sums, this calls for linear algebra. You shouldn't program a for loop and do this, but this is matrix vector stuff, and I should use library for matrix vector stuff, because if you do this yourself with a for loop, you are implementing linear algebra very inefficiently, which means it won't work on large collections. And I now show you how to do it for prediction. Figure it out yourself for training. This is what we computed. And this should look familiar now. This is just a little different now. I didn't write the words here, but just the index of the words, but otherwise it's the same thing. And this is, I think what should be this is a bit misleading. I'm just realizing this now, so please pay attention when you look at this later. This is not the same M as before. M is now, before it was the length of the document, the size of the vocabulary. Yeah? And note, if TFI, if a word doesn't occur at all, then PIC to the TFI is just 1, right? It's just to the power of 0, so it's just 1. So this is nothing else than what I have before, right? What this says is I have word number 3, so this is word number 1, 2, 3, 10,000. Word number 3 occurs 3 times, then I just have the probability 3 times here. That's what it says, just probability for word 3 to the power of 3. If I have the word 7 times, I will have that probability 7 times here. We have seen it in the example. If the word doesn't occur, this is just 1. And then I multiply it with this, and this I ignore. And this is just the number of occurrences, just term frequency. And we give you all the code that computes these numbers. Now, you should take the logarithm for, because otherwise these numbers become too small, and we can ignore this because it's the same for all C. We just want to find the largest one. Then what do we have? Then we have this number, right? If I take the logarithm of this one, the product becomes a sum, and the TF is, we have seen this earlier, right? It's actually, we've seen this in the maximum likelihood thing. P to the 5 logarithm becomes 5 times logarithm of P. So you get this here, and this, now you have a sum of products, and a sum of products is always matrix vector stuff. This is just the product of these 2 vectors. So I'm already basically telling you how to do exercise 2 here. This here is exactly, and this should be capitalized. This is the dot product of these 2 vectors. Just look at these 2 vectors, take the dot product, and it's TF1 times ln P1C plus TF2 times this, plus and so on. And here I have a 1 in the end, plus ln PC. Oh, this is also wrong. This should be ln PC here. Yeah. And this is for one class, so you have a dot product for one class, and if you can do this for all classes simultaneously with a single matrix vector product. So prediction, you do one matrix vector product where your vector is the document, the matrix just contains, and look at this, I mean this is just here all the probabilities for one class, and now you have this for every class, gives you a matrix. Single matrix vector product gives you all the things for all the classes, and then you can just read off the largest one. So prediction in naive Bayes, if you implement it yourself, it's like this. If you do it with matrix vector, it's a one-liner. It's a one line, and you have to find the largest entry. And it's very often like this. And in NumPy, if you know the right function, everything is one line. Training is not quite as simple. So here's the last slide. Just an overview over things, and please recall that we did for you this very nice cheat sheet. I think I said it already in the last lecture. So because the NumPy, SciPy, you need SciPy again because a large matrix, sparse, and so on. The documentation is huge, but you just need a subset, and this page here gives you. So just as a reminder, these things can be done in one line in NumPy. Multiply a matrix, this is always from the perspective of a matrix. Multiply it with a vector, transpose it, one line. You want to set it, that's a sparse matrix construction. You have given indices and values constructed, that's a one-liner. Component-wise addition, like multiply everything by 3, add 1 to every entry, it's a one-liner. Apply an operation, you have a matrix, you want to apply ln to every entry, it's a one-liner. Never ever write for loops. I mean, you can, right? You can do for all rows, for all columns, do this entry equals log this entry. It will take forever. Just do log matrix. It will do the right thing. Compute for each row the sum, for each column the sum. It's a one-liner. For each row, compute the largest value. sort each row, sort each column. It's a one-liner. Everything you can. You have a vector, you want multiple copies, like you have one row vector and you want it 10 times as a matrix. That's a one-liner. Yeah, and there's the cheat sheet. So that's it. It's a very nice method, very nice exercise. Any question about the topic or the exercise sheet? Anything in the chat? Oh, there was one question. Oh yeah, that resolved itself. Okay, so have fun with the sheet. See you next week. Bye-bye.